In this video, we are going to discuss about RLC circuit for DC excitation. So for that one, let's consider the circuit. Here a DC voltage source having voltage V is connected across series RLC circuit. At t is equal to 0, the switch is getting closed so that current will flow through the circuit. So that circuit is separately drawn over here. At t is equal to 0, the circuit become like this. I of t is the current flowing through the circuit. For simplicity, let's assume initial conditions as zeros. What are the initial conditions? Voltage across capacitor is assumed to be 0 volt and initial current through the inductor. Since it is the series circuit, the current through resistor is equal to current through inductor, which is equal to current through capacitor. That current is taken as 0. So that's why it is written as assume 0 initial conditions. Now, how many energy storage elements are there? There are 2 energy storage elements. So the order of the circuit is 2. So in order to see that one, let's apply KVL over this loop. So KVL equation become V is equal to R into I of t plus L into di by dt plus 1 by C integral minus infinity to t I of t dt. So here this integral part can be splitted into 2 parts, that is 1 by C integral minus infinity to 0 I of t dt plus 1 by C integral 0 to t I of t dt. So as initial condition is assumed to be 0, this part, that is 1 by C integral minus infinity to 0 I of t dt won't be appear. Clear? So that is initial current through the inductor, that is assumed to be 0. That reason is written over here why we are converting this into this part. So neglecting initial conditions only, we got this expression. So let it be equation number 1. Now we can, the equation consists of both the differential part and integral part. Therefore this equation is known as integro-differential equation. Now we can differentiate equation number 1 with respect to time. So differential of V, that is constant, with respect to time is 0, which is equal to L into d square I by dt square plus R into dit by dt plus 1 by C. Differential of integral is, that part will remove from here. So that become 1 by C I dt. Sorry, 1 by C I of t. So from this equation, differential equation, the order is, maximum order is 2. Therefore order of this equation governing this circuit is 2. Okay. So which is equal to number of energy storage elements as I mentioned earlier. Now recalling this circuit again, after t is equal to 0, the KVL equation is R into I of t plus L into di by dt plus 1 by C integral I dt. That is taken as equation number 1. Now as we discussed in RL and RC circuit, we need to take the Laplace transform of equation number 1. Laplace transform of constant V is V by S and R into I of t, small I of t, Laplace transform is capital I of S, and differential equation di by dt is S into capital I of S, so Ls into capital I of S plus 1 by C, and this integral I of t, that Laplace transform is capital I of S by S. Simplifying, we can obtain the equation number 2, that is equation number 1. After taking Laplace transform, we can obtain the expression for I of S as V by L all divided by S square plus R by L into S plus 1 by LC. Let it be equation number 2. Now we can see some important terms which we are going to study in coming semester. So first one is transfer function. Transfer function is defined as Laplace transform of output to, it is the ratio of Laplace transform of output to Laplace transform of input, assuming zero initial conditions. So at zero initial condition, Laplace transform of output divided by Laplace transform of input, that ratio gives transfer function. That terminology is termed as transfer function. It is also denoted by G of S. G of S. So here we are discussing second order system. So for second order system, there is a standard transfer function form. The general transfer function of second order system can be written as omega n square divided by a square plus 2 zeta omega ns plus omega n square, where omega n is known as natural frequency of oscillation and zeta is known as damping ratio. So here the denominator polynomial of this transfer function is termed as characteristic equation CE. So what is characteristic equation of the standard transfer function of second order system? That is a square plus 2 zeta omega ns plus omega n square. Now we can have this equation. This is current, this is response actually, that is output, and applied voltage is V. So anyway, this part S square plus R by L S plus 1 by LC is the characteristic equations of this system. Okay, RLC series circuit excited by DC voltage source. So this is the characteristic equation which we derived, and it is represented by equation number 2. And this is the characteristic equations, general form of these characteristic equations of second order system. Now we can compare these two characteristic equations. Why? Because both represent second order system. So S square plus R by L S plus 1 by LC is equal to S square plus 2 zeta omega ns plus omega n square. By comparing this term, omega n square is the corresponding term in our response is obtained as 1 by LC. So natural frequency of oscillation can be obtained as 1 by root LC. If you know the value of inductance and capacitance, you can easily find out natural frequency of oscillation by means of this equation. Okay. Similarly, by comparing the coefficient of S, when we are comparing the coefficient of S, 2 zeta omega n is equal to R by L. We know the expression for omega n as 1 by root LC. 1 by root LC. Okay. So R by L is equal to 2 zeta omega n. Substituting omega n as 1 by root LC like this, we can obtain the expression for damping ratio as R by 2 root C by L. So please note these two equations. One is natural frequency of oscillation can be found out by means of this equation 1 by root LC, and zeta damping ratio can be obtained by means of this equation R by 2 into root C by L. So this is very important. These two parameters are very important. Now recalling the expression for I of s as V by L divided by S square plus R by L into S plus 1 by LC, that is equation number 2. Here we can obtain, so this is a characteristic equation, this one is characteristic equation, that is nothing but a quadratic equation. So anyway, since this equation is second order equation, we can have two roots. Let the roots be R1 and R2. We can write down the roots in this form, that is S minus R1 into S minus R2. So this equation can be, that means denominator polynomial can be expressed in terms of root like this, where R1 and R2 is the root of this characteristic equation. Okay, denominator polynomial. As I mentioned earlier, this equation is quadratic equation. We can find out the root by means of this standard method, that is minus b by root b square minus 4ac divided by 2a. In this expression, that is denominator polynomial, that is separately written over here. So here A is 1, B is R by L, and C is 1 by LC. We can find out the root by means of this expression as mentioned here. And finally, we can obtain the roots R1 as minus R by 2L plus root R by 2L all square minus 1 by LC, and R2, here the plus become minus as mentioned here, and let these two equations be combined, and it is represented as equation number 3. Now we can call this term real part, that is R by 2L, as alpha, and it is expressed in terms of alpha, in terms of omega and theta as here, as mentioned here. So alpha is equal to R by 2L, this one. This can be expressed in terms of damping ratio and natural frequency of oscillation as mentioned in equation number 4. So that proof is written over here. So please go through it. So next important term is omega d. Here omega n is natural frequency of oscillation, that is the maximum frequency of oscillation in that circuit, and omega d is known as damped frequency of oscillation, and omega d equation is omega n into root 1 minus theta square. Now we can see that omega d can also write in terms of R and L like this. Omega d is equal to root 1 by ELC minus R by 2L all square. But in this expression for roots, we need root of R by 2L all square minus 1 by LC. But omega d is this one. So how to obtain this one from here? We need to multiply with root minus 1. So in equation 3 we need this term, but in equation 5, let it be equation number 5, this part be equation number 5, that is omega d. We need this part. How to obtain equation number, this part in equation number 3 by means of equation number 4, so by means of equation number 5. Here equation number 5 we need to multiply with root minus 1. So that become j omega d. Clear? That become j omega d. Why? Because root minus 1 is j, that is complex operator. Now considering equation number 4, that is alpha, here this part can be represented as alpha, and this part we can represent it by j omega d. Clear? Now the roots can be represented in terms of alpha and omega d like this. R1 is equal to minus alpha plus j omega d, and R2 is equal to minus alpha minus j omega d. Please remember, alpha is equal to theta omega en, and omega d is equal to omega n into root 1 minus theta square. Now we know the equation for I of s is V by L divided by S square plus R by L into S plus 1 by LC, that we can solve in this way, that is written as V by L divided by S minus R1 into S minus R2. Now what we can do is we can use partial fraction expansion. This become A divided by S minus R1 plus B divided by S minus R2. A can be obtained by means of this way, that is already discussed in class, and let's take that constant as K1, and B can be found out in this way, let that constant can be taken as K2. Now equation 2 can be written as I of s is equal to V by L divided by S minus R1 into S minus R2 as K1 divided by S minus R1 plus K2 divided by S minus R2. Let it be equation number 7. Now we can take Laplace inverse of equation number 7. We can obtain this equation, K1 e raised to R1t plus K2 e raised to R2t. we know what is R1. R1 is minus alpha plus j omega d, and R2 is minus alpha minus j omega d. So this is the general solution for equation number 2, that is I of t, current expression response. Now based on this discussion, we can discuss some terms which is coming in second order system, second order RLC series circuit. So first one is critical resistance. It is the value of resistance which determines the characteristics of the roots, whether the roots are real, or equal, unequal, imaginary, etc. That concept we can obtain from critical resistance. So we know the characteristic equation as a square plus r by l into s plus 1 by lc, and equation for IFS is we know this one, and roots of the denominator polynomials are r1 and r2. General expression is obtained as minus r by 2l plus or minus root r by 2l all square minus 1 by lc. So the critical resistance is the value of resistance at which this square root terms become 0. The value of resistance at which square root terms of above equation become 0 is called critical resistance. So at critical resistance, roots becomes real, equal and negative. Clear? So when this part is 0, the roots are minus r by 12 alone. Both roots become minus r by 12. Okay, so when this part is 0, the root becomes 0. R by 12 whole square is equal to 1 by LC is the condition for critical resistance. So under this case, what is the resistance value? That is the critical resistance, that we can derive as RCR as 2 into root L by C. Next terminology is damping ratio. It is the ratio which indicate opposition from the circuit to cause oscillation in its response. So whenever some oscillation is there in response, how much opposition is coming from the circuit itself? So that part is denoted by this ratio, damping ratio. So if theta is more, so damping ratio is denoted by theta. If theta is more, that is damping is more, there is more opposition. Clear? The more opposition is there for oscillation. That means there is less chance for oscillation in response if theta is more, and vice versa. So it is the ratio of actual resistance in the circuit to critical resistance. Theta is equal to R divided by RCR. As we derived earlier, theta is equal to R by 2 into root C by L. So this is very important. So next one is natural frequency of oscillation. If theta damping is 0, if damping ratio is 0, then there is no opposition to the oscillation. Then response oscillate at maximum frequency, then that maximum frequency is called natural frequency of oscillation. Under that condition, there won't be any opposition for the oscillation from the circuit. So we know the expression for omega n as 1 by root LC. So next important term is damped frequency of oscillation, which is equal to omega d, which can be obtained by means of this equation omega n into root 1 minus theta square. As I mentioned earlier, theta value is usually lies between 0 and 1. Therefore, omega d, the value of damped frequency of oscillation, is less than that of omega n, natural frequency of oscillation. So damped frequency of oscillation is also known as actual frequency of oscillation. So based on damping ratio theta, RLC series circuit can be classified into 4 categories. So one is undamped circuit, second one is underdamped circuit, and third one is critically damped circuit, and the last one is overdamped circuit. Let's see one by one. When theta is equal to 0, the circuit is termed as undamped system, undamped circuit. We know the general expression for I of t as I of t is equal to k1 e raised to minus alpha plus j omega d t plus k2 e raised to minus alpha. Here it becomes minus j omega d t. We know alpha is theta omega n and omega d as omega n into root 1 minus theta square. In this case, undamped system, theta is equal to 0, so alpha becomes 0. When theta is equal to 0, alpha becomes 0. When theta is equal to 0, omega d become omega n. So at undamped system, undamped circuit, damped frequency of oscillation is equal to natural frequency of oscillation. And when we are checking the roots are minus alpha plus j omega d. Alpha is equal to 0 when theta is equal to 0. So roots are pure imaginary, plus or minus j omega n. And as we know, e raised to j theta is equal to cos theta plus j sin theta. The response here I of t is e raised to j omega t and e raised to minus j omega dt. That part is only available. So the response contains sines and cosine terms. Okay. So response contains only sine, combination of sine and cosine terms. So the general format of natural response of undamped system can be written as K1, capital K1, it is constant which is determined by the circuit parameters, into cos omega nt plus j k2 sin omega nt. So when we are drawing the response, the current will oscillate at fixed frequency. The frequency is fixed and magnitude is fixed. So the response have oscillations with fixed magnitude and frequency. Such type of oscillations are known as sustained oscillation, as seen here. So next category is underdamped circuit. Under underdamped circuits, the value of theta lies between 0 to 1. And it is to be noted that when we deriving this expression, general expression, that is this part. So roots of the denominator polynomial is obtained as minus r by 2l plus or minus root r by 2l whole square minus 1 by lc. Underdamped condition occurs when this part, the roots become imaginary. That is r by 2l become less than 1 by lc. Under that condition, the roots contains both real part plus imaginary parts. Condition for underdamped system is r by 2l become less than 1 by lc. This part become more compared to this part. Under that condition, this part become imaginary and this part is real part. So the roots contains negative real and imaginary parts. Complex conjugate will come into picture. So the roots are minus alpha plus or minus j omega d. Roots are complex conjugate with negative real part, as I mentioned earlier. So we know the general expression for response I of t as this one. So equation can be obtained in this form: e raised to minus alpha t into k1 cos omega dt plus j k2 sin omega dt. Why? Because e raised to j theta is equal to cos theta plus j sin theta. By simplifying, we can obtain this equation. So here it can be seen that oscillation decays. There is no fixed oscillation with fixed frequency, with fixed magnitude and fixed frequency. Here as t tends to infinity, or as t increases, we can see that oscillation decays, as seen here. So next category is critically damped circuit. So critically damped circuit occurs when theta is equal to 1. Under that condition, this part, that is r by 2l all square become 1 by lc. So under that condition only we got critically damped circuit. R by 2l is equal to 1 by root lc. So we know the roots of the polynomial, denominator polynomial is generally expressed as minus alpha plus or minus j omega d. Alpha is this one and omega d is this one. At theta is equal to 1, we can see that theta is equal to 1. We can see that alpha is equal to omega n and omega d becomes 0. That means both the root contains only real parts, that is roots are equal and real with negative. Okay, so roots are minus omega n, both roots are minus omega n. R1 is equal to R2 is equal to minus omega n. So the expression become the response equation I of t become k1 e raised to minus alpha t plus k2 e raised to k2 into t e raised to minus alpha t. So this is the standard form for the response under critically damped circuits. So the roots can be, when we are plotting the expression, this expression, that is I of t, you can obtain this type of response. It is exponential as seen here. So next category is overdamped circuit. Overdamped circuit occurs when theta is greater than 1. So under that condition, R by 2L become greater than 1 by root LC. That means under this condition only overdamped circuit will come into picture. We know the expression for root as this one. So here we can see that j omega d, the expression for omega d is omega n into root 1 minus theta square. So j into omega n root 1 minus theta square is j omega d. That we can written as omega n into root theta square minus 1, as I mentioned in first part. So under this case, overdamped case, theta is greater than 1. So always this part is real only. There is no imaginary parts. So under overdamped situation, roots are real and unequal. Clear? Roots are real and unequal. The expression can be obtained in this way: k1 into e raised to r1t first root and plus k2 e raised to r2t. This is the standard form. So when we are plotting this expression as a function of t, we can obtain this type of curves, this type of graphs. So let's compare for the response for different values of damping ratio. Say this is a critically damped situation, theta is equal to 1. This is the response corresponding to critical damped system, and omega is equal to 2. We can see that the response is still exponential, but it is more sluggish and slow. As theta is increasing, the response, its final value is achieving at in order to obtain the final, reach the final value, it is taking more time. So as theta is more, as theta increases, the response become more sluggish and slow. So this is the response curve corresponding to overdamped system. So now we can conclude these three concepts, that is when roots are real and unequal. When roots are real and unequal, corresponding circuit is overdamped circuit. And when roots are real and equal, when roots are real and equal, it is critically damped circuit. And finally, when roots are complex conjugate, the response is underdamped. For overdamped circuit, theta is greater than 1. For critically damped circuit, theta is equal to 1. And for underdamped circuit, theta lies between 0 and 1. So this completes the derivation theory part of RLC series circuit excited by means of DC voltage source.